Hello, I am Shabaz Abid. This is General Physics 1 Lecture 4. In the previous lecture we have derived an equation of motion for the constant velocity and we have solved some examples. We are going to do the same thing for constant acceleration in this lecture. When acceleration is constant, the velocity versus time graph is going to be a linear graph. So, to derive the first equation of motion for constant acceleration, let us consider this velocity versus time graph. We know that the slope of the velocity versus time graph is going to give us acceleration. So in other words, the acceleration is rise over run of the velocity versus time graph, which is equal to delta v over delta t. So if I rearrange this equation with respect to delta v, it's going to be equal to a sub x times delta t. We know that the delta v is equal to final velocity minus the initial velocity, and the delta t is actually final time minus the initial time. Now most of the time the initial time is equal to 0, so we are going to consider delta t to be equal to the final time, which is going to be t. So if I substitute these two in this equation, I'm going to get vxf, which is the final velocity, minus the vxi, which is the initial velocity, is equal to a sub x times t. If I bring this vxi on the other side, it's going to become positive. So we have the first equation of motion for constant acceleration as final velocity is equal to initial velocity plus a sub x times t. This equation is then equation of this line. To derive the second equation of motion for constant acceleration, let us consider the same velocity versus time graph. We know that the displacement is equal to area under the velocity versus time graph. So let us divide this area into two sub areas, which is basically a rectangle and a triangle. We can calculate the a1 to be equal to initial velocity times delta t. So again, if I consider the delta t to be equal to t, the area 1 is going to be equal to initial velocity times t. The area 2 is going to be a triangle, so it's going to be half times base, which is delta t, times the height is going to be final minus initial velocity, because we have divided this two areas from initial velocity. So it's going to be half times delta t times final velocity minus initial velocity. Now we know again that the slope of the velocity versus time graph is acceleration. So final velocity minus the initial velocity is divided by delta t. So if I rearrange this equation, it's going to become vfx minus vix is equal to a sub x times delta t. Again, if I consider the delta t to be equal to t, considering the initial time to be equal to 0, so the area 2 is going to become half times base times, we are going to make this part to be equal to a sub x times delta t. So I am going to substitute this thing in place of final velocity minus initial velocity. I am going to get a sub x times t. So if I simplify it, it's going to become half times ax times t square. Now we know again that the displacement is equal to the area under the velocity versus time graph. So we just need to add the area 1 with area 2. So we will get basically a second equation of motion, which is going to be final position minus initial position, which is delta x, is equal to area 1, which is initial velocity times t, plus half times ax times t square, which is area 2. So this is the second equation of motion for constant acceleration. To derive the third equation of motion for constant acceleration, let us consider the same velocity versus time graph. So again, we know that the displacement is equal to the area under the velocity versus time graph. So this time let us consider the area 1 to be from here until here. So it's going to be equal to final velocity times delta t. Again, delta t can be denoted as t. So A1 is equal to final velocity times t. The area 2, which is going to be subtracted this time, is equal to half times delta t times this difference, which is basically final velocity minus the initial velocity. So again, we know the slope of the velocity versus time graph is acceleration, so it's equal to final velocity minus initial velocity divided by delta t. So if I rearrange this equation, it's going to become final velocity minus initial velocity is equal to a sub x times delta t. Again, the delta t can be denoted as t, so I'm going to get the area 2 if I substitute instead of final velocity minus initial velocity as a sub x times delta t, and delta t is denoted as t, I'm going to get the area to be equal to half times t times, instead of this, which is final velocity minus initial velocity, I will substitute a sub x times delta t. So if I simplify it, it's going to become half times ax times t square. So we have considered the area 1 to be from here till here. So we are actually calculating something extra, which is basically area 2. So the displacement is equal to the total area, which is from here till here, minus the area 2 is going to give me the area under this graph. So if I substitute, delta x is going to be final position minus the initial position is equal to area 1 is going to be final velocity times t minus half times ax times t square, which is area 2. So this is the third equation of motion for constant acceleration. To derive the fourth equation of motion for constant acceleration, let us consider the same velocity versus time graph. If we transfer this red shaded triangle to here, it's going to develop a square or a rectangle shaded area, which is green. The height of this rectangle area is going to basically be the average velocity, because it is in the middle of the final velocity and the initial velocity, and its length is going to be delta t. So the area of this green shaded region is going to be displacement, which is going to be now equal to average velocity times delta t. If I consider the delta t to be equal to t, considering the initial time to be equal to 0, and we know that the delta x is equal to final position minus the initial position, and the average velocity means final velocity plus initial velocity divided by 2. If I substitute all of these in this equation, I'm going to get the fourth equation of motion, which is basically final position minus initial position is equal to average velocity times t. In all the four equation of motion we derived, there was time as a variable. So let us derive an equation of motion, which is going to be our fifth equation of motion, without having time as a variable. So we know that the average velocity is final velocity plus initial velocity divided by 2, and we know that the delta x, which is the displacement, is equal to the average velocity times delta t. I can rearrange this equation with respect to delta t, so it's going to become delta x over average velocity, and if I substitute the average velocity, it's going to become delta x over final velocity plus initial velocity divided by 2. We know again that the acceleration is the slope of the velocity versus time graph, which is basically final velocity minus the initial velocity divided by delta t. So now if I substitute delta t in this equation and I rearrange it, I'm going to get in brackets final velocity minus initial velocity times in bracket final velocity plus initial velocity divided by 2 times delta x. So basically from here all the way here we have this form. So if I bring the 2 times delta x to the left, it will become 2 times a sub x times delta x is equal to. So if we have a minus b in brackets times a plus b in brackets, we can simplify it to be a square minus b square. So it's going to become final velocity square minus the initial velocity square. Bring the initial velocity to the left and rearrange this formula. It's going to give us the fifth equation of motion, which is going to have no time as a variable. So it's going to be final velocity square is equal to initial velocity square plus 2 times ax times delta x. To summarize all the equations of motions which we derived, let us see each equation one by one. In the first equation of motion, we have final velocity as a variable, initial velocity as a variable, acceleration as a variable, and time as a variable. It does not depend on the displacement. So if I'm going to have any three of these variables, I can get the fourth one from this equation. In the second equation, I have displacement as a variable, I have final and initial velocity as a variable, and I have time as a variable as well, and it does not depend on the acceleration. And again, if I know any three of these variables, I can get the fourth variable from this equation. In the third equation, we have again displacement as a variable, we have initial velocity as a variable, we have time as a variable, and we have acceleration as a variable, and it does not depend on the final velocity. So again, if I know any three of these variables, I can get the fourth variable from this equation. The fourth equation has again displacement as a variable, final velocity as a variable, time as a variable, and acceleration as a variable, and it does not depend on the initial velocity. So if again if I know any three of these variables, I can get the fourth variable from this equation. If you notice, all the first four equations have t as a variable. So the fifth equation of motion does not depend on t, and it depends on final velocity as a variable, initial velocity as a variable, and acceleration as a variable, and displacement as a variable. So if I know any three from these variables, I can get the fourth variable from this equation. If you observe equation 3, if I have a constant velocity criteria, which means acceleration is equal to 0, we have derived an equation of motion for constant velocity. But again, if I'm going to substitute a equals to 0 in this term, this will become 0, and I'm going to get the exact same equation of motion for the constant velocity which I derived in the previous lecture. Let's solve example 1. An airplane starts accelerating uniformly from rest to a speed of 100 meter per second in 25 seconds. What is the acceleration in meter per second square of the airplane? So the given variables we have here is initial velocity is equal to 0 because it is starting from rest. Final velocity is 100 meter per second in 25 seconds, so the time is also given to us. So we have three variables known here, and the required variable is acceleration. Based on the given and required, the first equation of motion is the most suitable equation to solve for acceleration, because we have final velocity given to us, initial velocity given to us, and time is given to us, and the requirement is acceleration. So if we know these three, we can get the acceleration from this equation. By substituting the final velocity as positive 100 because it is moving towards the right, initial velocity is 0 because it is starting from rest, and the time is 25 seconds, we are going to get the acceleration equal to 4 meter per second squared. Let's solve example 2. A bus starts moving from rest with a constant acceleration in a straight line until it reaches 50 meter per second. Its average velocity in meter per second is, so here we need to find the average velocity, and we know the two variables, which is going to be final velocity and initial velocity is equal to 0 because it is starting from rest. So based on these two given variables, we need to find the average velocity. In the second equation of motion for constant acceleration, this red part of this equation is actually the average velocity. So we just need to substitute the final velocity and the initial velocity and divide by 2. We are going to get the average velocity. So by substituting 50 and 0 divided by 2, we are going to get the average velocity to be 25 meter per second. Let's solve example 3. A train starts accelerating uniformly from an initial velocity v0. After 20 seconds, the velocity increases to 40 meter per second, during which it travels 600 meters. Find the car initial velocity in meter per second. So the given information we have is the displacement is equal to 600 meters, the final velocity is equal to 40 meter per second, and time is equal to 20 seconds, and the required variable is initial velocity. Based on this, the second equation of motion is the most suitable equation to solve this problem, because we have final velocity given to us, we have displacement given to us, time is also given, and we need to find the initial velocity. So by substituting delta x as 600, final velocity as 40, initial velocity is unknown, divide by 2 times the time is equal to 20, we are going to get the initial velocity equal to 20 meter per second. Let's solve example 4. A train leaves the station from rest and travels along a straight track. If after 20 seconds the train is 500 meters from the station, what is the acceleration of the train? The given information we have here is the displacement is equal to 500 meters, the initial velocity is equal to 0 because it is starting from rest, and the time is equal to 20 seconds, and the requirement is to find the acceleration. The most suitable equation of motion for this problem is equation number 3, because we know the displacement, we know the time, and we know the initial velocity, and we want to get the acceleration. So we can use this equation to get the acceleration. By substituting delta x is equal to 500, again delta x means final position minus the initial position. So we are going to consider the initial position to be 0, it's going to be at the origin, and the final position is 500, and by substituting initial velocity equals to 0, time is 20, acceleration is unknown, and the time is again 20 and it is squared, we are going to get the acceleration equal to 2.5 meter per second square. Let's solve example 5. The driver of a car traveling along a straight road sees that the traffic lights 80 meter away have turned to red. Given that after 5 seconds the car stops exactly at the traffic lights, what is the deceleration of the car? So the given information we have here is the delta x is equal to 80 meters. Final velocity is equal to 0 because it has stopped exactly at traffic lights. The time is equal to 5 seconds and the requirement is to get the acceleration. The most suitable equation to solve this problem is basically equation number 4, in which we know the displacement, we know the final velocity, and we know the time, and the requirement is to get the acceleration. So by substituting delta x is equal to 80, final velocity 0, time is 5, minus half a times 5 square, we are going to get the a equals to minus 6.4 meter per second square. Negative indicates that this is deceleration of the car, which is allowing the car to stop. Let's solve example 6. A driver of a car going at a constant velocity of 25 meters per second suddenly sees the lights of a barrier 40 meters ahead. It takes the driver 0.75 seconds to apply the brakes, and the acceleration during braking is negative 10 meters per second squared. Determine whether car hits the barrier. Initially, the car is going at a constant velocity of 25 meters per second. After 0.75 seconds, the driver applies the brakes, and the acceleration during braking is negative 10 meters per second squared. So there are two phases. One phase is constant velocity and the second phase is constant acceleration. So in the constant velocity, the car is going to cover some displacement, and also in the constant acceleration, the car is going to cover some displacement. If the car took total displacement to stop is more than 40 meters, the car is going to hit the barrier. But if the car took a total displacement to be less than 40 meters, the car will not hit the barrier. So to solve this problem, we have to solve it in two steps. The first step is going to be constant velocity, and the equation of motion for constant velocity is delta x, which is final position minus initial position, is equal to v sub x times t. So the final position is unknown, initial position is considered as 0 because we are going to measure the position when the car was at this distance of 40 meters from the barrier, is equal to velocity is 25 and the time of constant velocity phase was 0.75 seconds. So the total displacement for constant velocity is equal to 18.75 meters. In the second step, which is constant acceleration, the constant velocity becomes the initial velocity for the second phase, and we have acceleration and we know the car is going to stop, but at which distance or which displacement we still don't know. So in the second phase, which is constant acceleration, the time is not given to us. So if the time is not given to us, we can solve with the fifth equation of motion, which is final velocity squared is equal to initial velocity squared plus 2 times a times delta x. So the final velocity is 0, initial velocity is 25 and it is squared, plus 2 times negative 10, which is the acceleration. The final position is unknown, and we can consider the initial position to be the final position of constant velocity. So the initial position has now become 18.75 for constant acceleration. To solve this problem, we are going to get the final position of a car equals to 50 meters. So it took 50 meters of total displacement to stop the car from 25 meters per second to 0. the total distance traveled by the car is 50 meters, which is more than 40 meters. So therefore the car will hit the barrier. Let's solve example 7. A motorcyclist starts from rest with a constant acceleration of a equals to 4 meters per second squared for a time t1 equals to 15 seconds. Then it travels with constant velocity for time t2. If it passes a tree after traveling a total distance d equals to 870 meters, then t2 in seconds is. This example is again going to be solved in 2 steps. First step is going to be constant acceleration and the second step is going to be constant velocity. In constant acceleration, in time t1 equals to 15 seconds, a motorcyclist is going to cover some displacement. So if we know that displacement and we get the difference between 870 meters and this displacement, is going to give us the remaining displacement to be covered in constant velocity. In the constant acceleration phase again, a motorcyclist is going to have a final velocity. That final velocity is going to become a constant velocity for step 2. So step 1 is constant acceleration. We know it is starting from rest and it has a constant acceleration of a equals to 4 meters per second squared for a time t1 equals to 15 seconds. So based on this information, we can use this equation of motion to solve for the displacement covered, which is going to be equal to 450 meters. Now to get the final velocity, I have used the final equation of motion for constant acceleration. So I am going to get a final velocity equals to 60 meters per second. For step 2, which is constant velocity, the equation was final position minus initial position, which is delta x, is equal to v sub x times t. The final position is 870 and the final position of step 1 has become the initial position for step 2, is going to be equal to the final velocity of constant acceleration step has become the constant velocity for step 2. So it's going to be multiplied with t2, and by solving this equation we are going to get the t2 equals to 7 seconds. Let's solve example 8. A van moves at constant velocity of 50 meters per second. At school crossing, it overtook an officer who started his motion after 3 seconds from rest with constant acceleration of a sub x equals to 4 meters per second squared. When and where officer will overtake the van? When means time and where means position. Since it's a relative motion question, we know that when two objects meet, they are going to meet at the same position and at the same time, which means the final position of an officer is equal to the final position of the van. So to solve this problem, we have to consider the van calculation and the officer calculation one at a time. In a delay of 3 seconds by an officer to start his motion, a van is going to cover some displacement. Since it's a constant velocity, so the displacement delta x is going to be v sub x times t. So 50, which is the velocity, times 3, which is time, will give you 150 meters. After officer started its motion, we don't know the final position of the van, but we know the initial position of the van is going to be 150, is equal to, again the velocity is 50 and the time is t. If I bring 150 on the other side, it will become the final position of the van is equal to 50 times t plus 150. Now I have two unknowns and one equation. So now we need one more equation to solve this problem. For an officer, it started from rest and the acceleration was constant, which was equal to 4 meters per second squared. and we have to consider displacement in the equation of motion. So a suitable equation of motion is delta x, which is final position minus initial position, is equal to initial velocity times delta t plus half times a times delta t squared. Now why I have included delta t? It's because there is a delay by an officer of 3 seconds, which means what? There is going to be an initial time of 3 seconds by an officer. So final position is still unknown, minus the initial position is 0 for the officer, is equal to the initial velocity, it's again 0, in brackets delta t is basically final time, which is t, minus the initial time, which is 3, plus half times acceleration, which is 4, times in brackets t minus 3 whole squared. So you will get another equation with respect to final position. So the final position of the officer is equal to 2 times t minus 3 whole squared. So the final position of the van is going to be equal to the final position of the officer. So if the left hand side of both equations are equal to each other, it means the right hand side are also going to be equal to each other. So equating the right hand side of both the equations, we will have 50 times t plus 150 is equal to 2 times t minus 3 whole square. If you are going to simplify this, it will become 2t square minus 62t minus 132 equals to 0. This represents a quadratic equation. To solve quadratic equation, we have to use quadratic formula, and we are going to get two roots. The first root is going to be 33 seconds and the second root is going to be minus 2 seconds. Time is always positive, so the time is going to be equal to 33 seconds. If I substitute time equals to 33 seconds in any one of these two position equations, I'm going to get the final position equals to 1800 meters. Let's solve example 9. Car A moves with constant velocity v equals to 10 meters per second directed parallel to the positive x-axis. A second car B starts from the x-axis with 0 speed and constant acceleration a equals to 2 meters per second squared and moves parallel to the y-axis. If both cars meet each other at point P, find D. This problem consists of two cars, but one car is moving parallel to the x-axis and one car is moving parallel to the y-axis. And this is the top view of these two cars. So car A is moving with the constant velocity criteria and the car B is moving with the constant acceleration criteria, and they are going to meet at point P. So again, it's a relative motion question. We know that when two objects meet, they are going to meet at the same position and at the same time. So based on this, car A is moving with a constant velocity, so we know the delta x is equal to v sub a times t. So the final position of car A is known, which is 100 meters, and the initial position is 0, is equal to velocity, which was 10 times t. So we can get the time for A equals to 10 seconds. So again, it's a relative motion question. Two objects meet at the same position and at the same time, which means the time it took for a car A to reach at point P is 10 seconds. It's going to be also 10 seconds for car B. So the delta y, basically this displacement in this direction, is equal to initial velocity times t plus half times a times t squared. We don't know the final position, which is d. We know the initial, it has started from the x-axis, which is 0, y is equal to 0 at this location, is equal to initial velocity, which is 0 because it started from rest 0 speed times the time is 10 plus half times acceleration times 10 squared. So we are going to get the d equals to 100 meters. Thank you, and I will see you in the next lecture.